was the perpendicular bisector. And the way you know you're talking about a perpendicular bisector is that you have these two sides are the same, and then this is perpendicular. The perpendicular bisector does not necessarily hit the vertex of a triangle. It might if the triangle is equilateral or isosceles, but it doesn't have to. Okay. Then you have the angle bisector, and you know you have an angle bisector if these two angles are identical. So this is the same as this. And it comes straight out of the vertex. Now it doesn't have any kind of relationship to the other side. It just hits where it hits. But the angles are the same. Okay, so for example, if this was 5, then this is 5. If this is 20, then this is 20 kind of thing. Okay. Then you have a median. And a median hits the midpoint. So these two sides are the same, and the difference between a median and a perpendicular bisector is that the median always has to come out of the vertex. It may end up being perpendicular. A median can also be a perpendicular bisector if you have, like, say, for example, an isosceles triangle. But it doesn't have to be perpendicular. It can be any angle at all, as long as it hits that midpoint. And finally, we had the altitude, and the altitude comes from the vertex and is perpendicular to the other side. It doesn't have to be inside the triangle, though. Remember, if we had like a really obtuse triangle, the altitude could fall outside. Okay? If we have three perpendicular bisectors, they meet at the circumcenter. And it's equidistant from each vertex, so each of these lengths are the same. And then you had the incenter, and that's equal distance from the sides. Okay. Then when you have the medians, we have the centroids, and remember this one, if this is 1, this is 2. So let me actually change that. Make that. If this is x, this is 2x. Okay. And then you have the orthocenter, which is where the altitudes hit, and it does absolutely nothing at all. There's no special relationships amongst the sides, no special relationships amongst the angles. The orthocenter is just the name they gave to where the altitudes hit. But so we're nothing special. Okay, and so you need to remember that so that you're not racking your brain trying to figure out what the orthocenter does. It doesn't do anything. It's just there. Now that we've discussed all that, we're going to leave those behind a little bit and move on to inequalities in triangles. And again, the concepts here are not going to be really, the concepts aren't not going to be really hard concepts. It's just remembering. It's just this chapter, there's just a lot of memorization more than there's a lot of difficult concepts. Not like the proofs, where the proofs were hard, or, you know, the other stuff we've done where, you know, the kind of the math got hard. This is just that you have to remember a lot. So, you know, that can be kind of hard, I guess. But, okay, what we have right here is the technical math definition of what it means to have an inequality. Okay? And that is for any two real numbers, A and B. A is greater than B if and only if there's some other number C that if I add it to B, A will equal B plus C. Okay? Non-math definition of an inequality. Some numbers are bigger than others. Okay. We have greater than. We have less than. We have greater than or equal to. And we have less than or equal to. Okay. When we're talking about angle inequality, what we're talking about is what occurs when one angle is larger than another. And that's their measures in degrees. All right, comparison property of inequality. This is just that A equals B, A is less than B, or A is greater than B. It has to be one of these three things. You can't have anything else. You're either equal, you're less than, or you're greater than if you're a number. I should say, though, this is in the real number system. In some other number systems, this is not true. So comparison property is pretty simple. You're comparing two numbers, and when you compare them, they're going to be equal, less than, or greater than. Okay. Then you have the transitive property of inequality, which is the same kind of idea as the transitive property of equality or congruency. You have if A is less than B and B is less than C, then A is less than C. Okay. Or if A is greater than B and B is greater than C, then A is greater than C. Okay. And again, the way you recognize transitive when you see it is this bit in the middle that matches B and B. And then these signs have to be pointing, the arrows have to all be pointing the same direction. Okay, but that's transitive property. And then we have addition property, which says if A is less than B, then A plus C is less than B plus C. So I can add the same thing to both sides, and it doesn't change the equality or lack of. And you also have if A is greater than B, then A plus C is greater than B plus C. So again, add the same thing to both sides, doesn't change the direction of the arrow. And finally, you have the subtraction property, which is basically the exact same thing, but instead of adding, we subtract. I know, right? Now, you will notice that I do not have on here a multiplication or division property of inequality. And that's because if I multiply or divide by a negative, it flips the inequality. So it can't be a real property, because if I multiply by a positive, it would work, but if I multiply by a negative, it won't work. And it has to work for both. So there's no multiplication properties or division properties with inequalities. Okay, did everybody get a chance to get them written down? Okay. We've seen this, the exterior angle sum, which told me that the measure of angle D is equal to the measure of angle A plus the measure of angle C. Oh wait, I'm doing angles. I meant D, not measures, sorry. That's D degrees. So little d is equal to little a plus little c, number-wise. So if this is 150, these two numbers will add up to 150. So let's say if I say A is equal to, let's that's about 45, and C is equal to 36, then D would be 45 plus 36, which would be 81. Okay, that's way not right, but whatever. Do you get the idea, though? Remember this? Seems familiar? Okay. We now have a theorem called the exterior angle inequality, and that is that the measure of any exterior angle in a triangle is greater Okay, so this should make sense. Okay, the measure of an exterior angle of a triangle is greater than the measure of either of its corresponding remote interiors. So remember that this exterior goes with these two remote interiors. If A plus C equals D, then it only makes sense that D would have to be bigger than either A or C. So angle D is greater than, sorry, not angle D, little d, is greater than A, and it's greater than C. Okay, and this is true for any exterior angle. You draw any exterior angle on any triangle, it is going to be bigger than either of the angles on the other side. So here's how we use it. We're going to list all of the angles that meet the following conditions. We want to be less than angle 7. Well, here's angle 7. Angle 7 is an exterior angle to two triangles. Angle 7 is exterior to this smaller triangle, and angle 7 is exterior to this large triangle. You guys see that? So starting with the small green triangle, so we'll use green. Angle 7 is greater than angle 5 and angle 4, because those are on the opposite side. I'm not going to use yellow because that would be silly. How about orange? And for the big yellow triangle, it's greater than angle 1. And then this angle is the yellow triangle. Well, that's 2 plus 4, right? If it's greater than 2 plus 4, but it was already greater than 4, that means it's also going to be just, greater than just 2 by itself. Does that make sense? So it's going to be bigger than angles 5 and 4 and 1 and 2. Now angle 6, angle 6 is an interior angle. Okay, let me erase all this really quickly. Angle 6 is interior to two triangles, but if we look at both triangles, like if I look at this triangle, I have this exterior angle where the line is continuing. If I look at this triangle, I have this exterior angle. Does that make sense so far? So angle 3 is exterior to the small triangle. Angle 8 is exterior to the large triangle. And an exterior angle has to be an extension of a side. So even though this angle 2 is not inside this yellow triangle, it's not an exterior angle because the yellow triangle side is not extending to make it. Does that make sense? Okay, so we're looking for the angles that are larger than angle 6. Angle 3 is an exterior angle, so that's larger. And angle 8 is an exterior angle, so that's larger. We want angles that are less than angle 1. Well, here's angle 1. And angle 1 is outside of this triangle. Okay. So, angle 1 is outside of the big triangle. We're looking on the opposite side, so we have this angle and this angle that'll be less than angle 1. Well, these two together are less than angle 1, so individually they're also less than angle 1, correct? So I have angle 3, angle 4, angle 5, and angle 6. I would list both because it's two separate angles. So I wouldn't like add them together and say that was angle 7 or anything. So it's angle 3 and 4 together that's less than 1, so individually they're also going to be less. That's just like saying if you and I together had less money than, say, Patrick over there. Individually, we would both still have less money. Okay. Yeah, well, this is like a triangle inside of a triangle, so we can kind of ignore this part right now because we're just talking about the big triangle. Okay, so if we get rid of all of that and to go to the next one, we're looking for angles that are measuring greater than angle 8. Now angle 8, again though, is in the big triangle. And we have two exterior angles to this triangle. We have angle 1 and angle 2. But angle 1 is right next to angle 8. Our theorem is only for the angles on the opposite sides of each other, so opposite sides of the triangle. So if we look at angle 2 here, angle 2 is greater than these two angles. So angle 2 is greater than angle 8, and that's the only one we know for sure. Like angle 1 looks like it's bigger than angle 8, but without, we don't know for sure that this is all drawn to scale. The only one we can say for sure is greater than angle 8 is angle 2. Because of the theorems, yeah. Okay, so for this one, angle 1, in the green triangle we have 2, 4, and 7. And angle 8 here, because these are on the opposite side. And then in the orange triangle we have 2 and 3. Well, we already listed 2, so 3. And then in the blue triangle we have 2 and 4 and 5. We already listed 2 and 4, so we can just say 5. Questions on that one? Okay, less than angle 9. So we're looking at angle 9 as the exterior, and we're going to look to the 3 triangles here that have angle 9 as an exterior, and you want to go to the other side. So in this one, there is not one. So we just have 2, 4, and 7. Over here we have 6 and 7, but we already had 7, so we just say 6. And then over here we had 4 and 7. But we already have those, so you don't have to list them again. No, that's just list them. This isn't grammar class. Okay, greater than angle 5. So we're looking for the angles on the outside, on the opposite side of a triangle from angle 5. So first I'm going to start looking at my angle 5 triangle. So here's an angle 5. Angle 1 is bigger because it's on the outside. And then I come around. Here's an angle 5, angle 3 on the outside. And this is an angle 5, but that's already on the outside, so I'm not counting it. And that's it. And then I do the same thing for angle 8. So I have 1, 2, 3 triangles where I have to consider angle 8. And I have 1, 2, 3 external angles on those. So angle 1, angle 5, and angle 3. Okay. What we have is that the longest side is across from the largest angle. And we have that the shortest side is across from the smallest angle. So if this is my largest angle, this is my longest side. If this is my smallest angle, this is my shortest side. So if I know the measures of the angles on the triangle, so like, let me draw a triangle real quick. Okay. And I know that, say, this is 30, and this is 70, and this is 80, let's just say. Obviously not drawn to scale. But I know then that this is the longest side, and this is the shortest side. Because 30 is the smallest angle, so that tells me the shortest side. 80 is the largest, so that tells me the longest side. Likewise, going the opposite direction, if I know the side lengths, so if this was, say, 10, and this was 20, and this was 18, I would know that this is the smallest angle, and this is the largest angle, because they're across from the smallest and the largest side. So I would be able to put the angles in numerical order, or put the sides in numerical order, even if I didn't have those numbers, as long as I had the numbers for the other one. Does that make sense? List the angles from smallest to largest. Smallest size, smallest angle. Largest side, largest angle. So this makes the angle in the middle. Ta-da! Smallest side, smallest angle. Largest side, largest angle, so that makes this angle in the middle. That's not an angle. Ta-da! I was just testing you. 3 is smaller than 4. That's the smallest angle. You know what I did? I looked at that, and I think I saw that as a 7 instead of as the 3. I don't know what I did. Any case. Better? Smallest to largest. Same thing if I know the angles. Now, I don't know this angle up here, but I do know that a triangle is 180, so I can take 180, and I can subtract 45, and I can subtract 56, and that tells me that this angle is 79. So I did 180 minus 45 minus 56, which tells me that this is the largest side, and this is the smallest side. So I have FH, FG is in the middle because it's not across from the largest or the smallest, and then GH is the largest. And likewise, this is 90 and this is 50. So this is like 40, 39. So largest, smallest. So WY, YX, and WX.